Hello, Jung. How are you doing?
Good. How are you?
All right, just prepping for class.
So I have a quick question.
Go for it.
Our next exam is not in person, but it is under Respondus, the lockdown browser, correct?
I haven't completely decided on that. In general, I usually keep my online tests, other than like if I have no choice but to administer it online. I usually keep them completely open, so you're allowed to use notebooks, notes, books,
I see.
and of course equation sheet and the internet. You're even allowed to do Google searches. So that's normally the way I do my online tests. I
Uh-huh.
might decide to do it with Respondus and the lockdown browser, just because it would, and the monitor, Respondus monitor, for one of them, but I haven't decided to do that yet. I know the final exam will be done that way, where either you're going to have to take it during lab, and like we did today with the lockdown browser, or you might be able to take it at home, but you'd have to use a Respondus monitor and browser.
I see. Okay.
But
I think
I'll
some
let
people
you know
were curious
earlier.
about it.
Yeah, I'll let you know. What it used to be is I usually only had two that were considered proctored. There was a midterm and a final, and that was worth 45% of your grade.
Oh
This
wow,
semester,
okay.
I've managed to make a category that counts. It was last time it was midterm 20 and the final 25. Now what I've done
Mm-hmm.
is I said all the face-to-face tests will be worth 20, and the
Mm-hmm.
midterm, I mean the final exam will be worth 25. So I might
Okay.
even be able to, make that more important, and instead of 25, maybe make it 35, and then just have nothing but uh, basically somewhat face-to-face tests, either by Respondus monitor or by lockdown browser with someone watching you.
Okay. Got it. Got it.
Okay. Sorry about
That's
not being able to give you a straightforward answer.
all right. It's okay. No, that was good. Thank you.
No problem. You're welcome. We got more people coming in. More people. Hello, Gabrielle. Maybe we only got a couple of minutes left. They should More people should have been here by now. Uh, I Hopefully Kevin told you guys. I'm not sure. Actually, come think of it, I don't think I ever told Mr. Mitchell about it. But your test that you took today, the correct answers will be available for like 24 hours, and that's about it. So make sure if you want to redo it, or you want to have any kind of record of it, what you want to do is go ahead and take screenshots of it with the right answers, and then that's something you can work on to make sure you really understood the test. Even if your grade wasn't that great today, that would still be a good thing to learn how to do, because I think you'd probably realize if you take away the stress of the test, you might have even done better. I will ask that you guys not share that with anyone. Don't give it to, a nephew, a cousin, a friend, or anybody else in later classes, because I might use those same questions again. And if those same questions get out, that sort of defeats our system of test banks, which obviously the author wouldn't be happy with. Uh, and, teachers that go to use it wouldn't be happy with it. I don't mind you guys in general seeing the answers if you're actually working these problems and you find the answer online. One, you don't necessarily know that the answer is correct, and two, uh, really that's just showing good work if you do it. So if you happen to luck upon doing the exact problem that comes out on the test, that's great that you happen to remember the answer. You just have to rework it again when you do the test, because sometimes they'll just change a small number and use one from the book. So,
Okay. Got it.
thank you. Hello, Solana. All right, we got about 1 minute left before I get cracking. Go on. Hello, Bohan and Drew.
Hey, how are you doing, Mr. Younger?
Not too bad. Hopefully you guys all did really wonderfully on your test. I hope you all made high A's or at least a B or something. Obviously not everybody will, but it'd be best if they did.
Yeah. Thank you.
You're welcome. All right. Well, it is time, so I guess I should go ahead and get started. Obviously people straggle in here as time goes by. So what we're doing is we're trying to finish up chapter 19 today, and we've essentially done everything through 19.5, and we even started talking about 19.6. So we have some knowledge of the first law of thermodynamics. I want to reiterate that the first law of thermodynamics really is just a restatement of conservation of energy. So that's another version of the first law of thermodynamics. And if you want to take into account what we learned from Einstein's relativity, you could say mass dash energy is neither created nor destroyed. And what we mean by that is Einstein showed us that not only is E equal mc squared, but E is equal to mc squared for every energy. So even when you burn a tank of gas in your car, if you were able to weigh the gas before you burn it and then weigh all the residue left through your engine after burning that one tank and all the stuff that came out of the exhaust pipe, if you were able to actually do all that and determine that mass to any number of decimal places, what you'd find is that the mass was not conserved. So this is, I think it was Joseph Priestley did the experiment to convince himself that after a burn, the mass of all the bits weighed exactly the same as the mass before the fire. So with a gas tank though, and let's say 16 decimal places or something like that, if you had that kind of precision, you could actually detect that there would be in fact a loss in mass from burning that tank of gas. And if you were to take that loss in mass and multiply it by the square of the speed of light, which is basically 200 million meters per second, you would get exactly the amount of energy that the car was able to create from it. So in other words, that lost mass was automatically converted to energy. And that's actually where the energy from the gas came from. So that's something that I didn't get when I first took relativity or when I first ran into relativity. And in fact, I don't even think I got it till I really started studying it on my own quite a bit, like in grad school. But that's a fact. Whenever there's an energy release, that's a result of some change in mass, and that change in mass times c squared is the energy released or absorbed or whatever happens. So we're going to start off with this version of conservation of mass dash energy, which we call the first law of thermodynamics. I will reiterate what it is. So let's start by letting me share my screen with you guys. Share screen. Waiting for it to law. Okay, we're good there now. Cool. So I've gotten some problems written up already. What I'm going to start with in actuality, I'm going to try to copy all this stuff. So this is the first problem I'm working, but I'm actually in the process of trying to copy it over to a different page. It seems like this particular point in time, it's not interested in doing anything. Maybe it's because my pencil's not. Oh, nope, it's not that. No, it's not that. Let's do this. Why is it not doing anything? Okay, so that didn't work either. Oh, well, I'll do the pages out of order. So what we learned about the first law of thermodynamics is this. This is first, whoa, no. This is the first law of thermodynamics. And again, we write this differently than they do in chemistry. Specifically, chemistry uses sort of a different idea of the work part of it than we do. Hence, that forces us to have a different sign. But what it is we have delta E, the internal energy, which often is called U. So don't be surprised if you see a delta U somewhere. We're using E because we don't want to confuse it with potential energy. That is actually equal to the heat added minus the work done by the system. So this is heat added to the system, which you have to define very precisely when you go to solve a problem. And this is work done by the system. However, you can actually widen it to take in the full breadth of what we learned from James Prescott Joule, specifically that mechanical energy and thermal energy are the same thing. And the way you'd expand that then is you'd say delta K plus delta U, which could include a lot of different potential energies, plus delta E internal is equal to Q minus W again. So that's also another version of the first law of thermodynamics, but taking into account all that other stuff. Similarly, we got this here. Now, I also will occasionally use a symbol like this one, which is actually dE internal is equal to d bar Q minus d bar W. And the reason why I put a bar on there is when you see a D, E, you know that you could in principle integrate it and get E, right? Well, there's no such function Q that's like an equation of state or anything that you can integrate to get Q out, and similarly for work. So that's why we have to put those bars on it. But that comes in handy. You can just treat those as like deltas, but the deltas are assumed to be very, very small. So that's what we learned last time in terms of the first law of thermodynamics, and that's about as far as we got. The main thing is I wanted you to understand that work done by the system is why the sign is negative there, whereas chemists generally use work done on the system. So let me turn back to the page with the example on it. So here's the question. It says 3,000 joules of heat is added to, that's supposed to be a gas, but to the gas in the cylinder. No, I guess that works. To the gas in the cylinder at 1900 joules of work is done by compressing the gas. What is the change in internal energy of the gas? So here's our solution. So we have delta E internal is equal to heat added minus the work done by the system. When you're actually compressing the gas, you're actually doing work on the system. So that means we've been told that Q, which is actually added to the gas, assuming the gas is our system, is 3,000 joules, but the work is being done on the system, so it's actually negative 1,900 joules, which gives us delta E internal is equal to 3,000 joules. And I'm going to pretend like that's 4 sig figs, as well as the 19 has 4 sig figs. And I'm going to say minus negative 1,900 joules. And of course, that's going to give you 4,900 joules of change in internal energy. Now that could be represented by just the average kinetic energy of the center of mass of the atoms and molecules that make up the system. But that's sort of all that's going to happen if your gas happens to be a monatomic ideal gas. If it happens to be diatomic or polyatomic, then other things can happen. So not only will the center of mass of the molecule or atom move left, right, in, out, and up, down, that's your 3 dimensions, it will also rotate about a particular bond, rotate about an axis perpendicular to that. And if you actually get hot enough, it'll actually cause the atoms to vibrate next to each other. So you ultimately get like 1/2 mv squared for v sub x, v sub y, and v sub z, meaning v squared is equal to v sub x squared plus v sub y squared plus v sub z squared. But as the temperature gets higher, you can actually cause, say, a diatomic molecule, if it's oriented like this, where there's an atom on that side and that side, then it could in principle rotate this way, which is a 1/2 I omega squared, but it could also rotate this way, which is another 1/2 I omega squared. It could rotate this way, but the atoms are so small that's not a significant bend for the energy, so that's not going to happen. Now, if you raise the temperature even further, instead of just having those 5 degrees of freedom, you can get 2 more degrees of freedom. One of those from the kinetic energy of the individual molecules on the end in their motion, but also the 1/2 kx squared as a result of basically them acting like a string separating them. So in that case, you actually come up with 7 what we call degrees of freedom. So when you change the internal energy, the equipartition theorem says each one of those bends is equally valid, and since the number of atoms or molecules is so large, you expect that it will have exactly the same amount of energy in each of those bends. Now, what we found on an experimental basis is, yeah, that's true, but it seems that gases often do not engage that second set of degrees of freedom or that third set of degrees of freedom until the temperatures get quite high. So that's another scenario. Now, let me see if I can copy this next example. So I'm going to see if it'll let me. Probably won't, knowing my luck. Anybody know why it's just telling me that I can take a screenshot instead of, I would think I could just click on this and highlight everything or move it. Why is it not saying copy or something like that? Anybody know? Okay, so that does not appear to be helpful to me at all. Maybe this. Let's see if it does now. I just clicked on something that sort of changed the view I was having, so I'm hoping I can use this now. It looks like it's just randomly changing crap. That's not helpful at all. Whoa, no, did not mean to do that. Again, it's just taking the screenshot. It's offering me to take a screenshot, not anything else. Okay, so I guess I'm just going to have to do it here. So in the previous example, what would be the change in internal energy if the gas did 1900 joules of work by expanding in the cylinder? So in this case, instead of like a cylinder being compressed, which is work being applied to the system, this is the system doing work. And in that case, we have solution. Delta E internal is equal to Q minus W, which in this case, the Q is still positive because we didn't change anything. So it's still 3000 joules minus, now instead of minus negative, it's minus the positive 1900 joules. because in this case, the work is actually being done by the system. So basically you're putting some energy into the system via heat, but the gas is actually, say the system or the gas or whatever is actually expanding. And because of that expansion, it's doing work and losing some of the potential increase in internal energy. So the answer ends up becoming 1,100 joules. So that is the answer for this one. And this is the answer for this one. Any questions on that? I'll try to get these things in the right order before I upload them, but right now I don't know why it's not letting me do what I normally do, which would be highlight that page or the text on that page and then move it, but it's not doing that now. So if y'all think of anything, let me know. All right. So that's two quote unquote chucker questions, if you will, regarding thermodynamics and specifically the first law of thermodynamics. This is like the easiest of the easy, supposedly. So hopefully that's not too bad. See if I can move this thing a little bit. There you go. That helps me. I'm also moving the little bar that has all y'all's names and pictures on it so I can get to my window, which is not letting me resize for some reason now. So that's super helpful. Nothing's working ever. Okay. So now that we got that, we can start another problem. So I just mentioned how these other terms can come into play. So let's work at this problem. An AR-15 that fires a 556/.223 space card, not space, Jesus me. Maybe I can erase it now. Let's see. That word space. I dictated it instead of typing it because I thought that would be faster, and it was. The downside is that it picked up the word space. Dang it picked up the word space again. And that cartridge has a mass of about 2 grams. I'm specifically talking about the projectile part. Obviously, the bullet itself with the shell casing and the powder weighs more. But the projectile has a mass of about 2 grams, which I'll assume I have 3 sig figs on. And the muzzle velocity is over 1,100 meters per second. I looked it up as 1,140 meters per second in one case, and it goes down to as low as like 970, but that's still pretty fast, even for the largest heavy and heaviest round projectile being fired. So after the projectile passes through a small tree, its velocity has been reduced to 550 meters per second. How much energy was transferred to the system? So we're doing that now. We're going to try to work out this problem. And what we know is, one, we've got to define our system well. So our system is going to be the bullet in the tree. So first off, system is the bullet plus the tree. And with that in mind, now we can say our first law of thermodynamics is delta K plus delta U plus delta E internal is equal to Q minus W. Now, in this scenario, since the bullet and the tree is our system, there's no external system applying any heat and no external system doing any work. So in fact, both of these quantities, Q and W, are 0. Not only that, we're looking at it for a short period of time, so the height shouldn't change, which means the delta U will be 0. So ultimately, we're just left with delta K plus delta E internal is equal to 0. And what we want to find is basically that delta E internal. So kinetic energy, as we know, the symbols, when they say delta, almost always means final minus initial. It essentially always does in physics, but sometimes, like I showed you before, when I use Q lost equals Q gained, that was a time where you flip the order to make sure the signs all were positive. In this case, I'm just sticking to old school. So I'm going to say 1/2 times 0.00200 kilograms. So that's 2 grams converted to kilograms, of course, times 1100 meters per second squared minus 550 meters per second squared plus delta E internal. All that adds up to give us 0. So any questions on that? Everybody understands what we're doing here and where this bullet stuff came from and all that good stuff. So the change or the energy transferred really is the internal energy. So I'm going to say the delta E internal, which is what we're looking for. I'm writing this down now, so we have that sort of the guide of what we're trying to solve for. So I'm actually solving for delta E internal. In that case, delta E internal is equal to the negative of the change in K. So notice they were both on the same side. So if I pull the kinetic energy term to the right-hand side, it'll be negative. So it'll be 0.00100 kilograms. In other words, I went ahead and multiplied by the 1/2, and then that's going to be 1100 squared minus 550 squared, which is 121 times 10 to the 4 meters squared per second squared minus 550 squared, which is 3025 times 10 to the 2 meters squared per second squared. I know that's not a traditional way to write this stuff, but it's a way that works, so you can see exactly what I got. So if I take that 1210000 and subtract from it the 302500, I get 90,000, or excuse me, 907,500. So this quantity is 907,500 meters squared per second squared. And notice a kilogram times a meter per second squared is a Newton, but this is a kilogram times a meter squared per second squared. So that's actually a joule, which is what we want. So I'm now going to multiply that by 0.001, and that's going to give me 907.5 joules, and that's actually a negative on it. Actually, that should be a positive on it because I'm doing the negative of the, oh yeah, yes, sorry about that. Okay, so any questions on, I see what I did. Notice I actually did my velocities in the wrong order. Sorry about that. I wish someone would have pointed that out. It's not that it's your fault. I mean, by stretch of imagination, that's clearly my fault, but I'm just saying I did make a boo-boo here. Let's change that real quick. The final velocity, of course, is when it left the tree, and that's 550. And the initial velocity was the muzzle velocity, and that was 1,100 meters per second. And then, of course, that makes this become a positive answer. And this right here, not letting me copy anything. So let's do it this way. 121 times 10 to the 4th is going to be 3025 times 10 to the 4th, or 10 to the 2. 3025 times 10 to the 2 minus, whoa, 121 times 10 to the fourth. Eat that. 1, 2. Still not big enough. Let's say. Damn. Stop that. 1, 2, 1 times 10 to the fourth. Okay. So that should give the same answer, only negative there. And of course, that turns out to be positive 907.5. So that's the actual energy transferred between the two. So you end up getting an increase in total internal energy. Partly the internal energy of the tree will increase, as well as the internal energy of the bullet, because both of them are going to warm up. Any questions on that? All right, so that's pretty straightforward problem. Notice how I did put the delta K on the left and then the delta E also on the left, and then all that delta K plus delta U plus delta E internal, all of that was equal to Q minus W. That's the key thing to understand. Now that we've done that, I will tell you that the vast majority of the vast majority of thermodynamics, when you take a class, because basically if you become like a physics major or an engineering major in many areas, basically just about every chapter or every major topic we covered in this 2-semester course will be a separate course by itself. So there'll be a whole course on Newton's laws of motions and kinematics, and those would be called statics and dynamics. In physics, we just call it mechanics. There'd be a whole course in electricity and magnetism that's also 2 semesters. That's called electrodynamics. There'll be one in quantum mechanics. There'll be one in thermodynamics. There'll be one in something called statistical thermo. In that type of course, the first, or I should say, a lot of times the first week is just learning a bunch of terms, but sometimes they spread it all throughout. But the main thing is we do have some terms we got to learn. So I wrote them down here. And you can actually record them and then write them as I explain them to you. So one process that can occur is called isothermal. It will not let me highlight anything anymore. Maybe if it lets me edit. There it is. Okay. Yay, finally got something. No, I don't want that. I want heading 3. There you go. Isothermal. And isothermal, you might recognize the word iso meaning equal. And then there's a matter of what do you mean by thermal? In this case, it means temperature. So what I'm going to say is isothermal means a process at constant temperature. Okay. Another thing that'll come up is a heat reservoir. So, for instance, one thing you might have noticed if you were paying somewhat of attention, you might have noticed that houses nowadays, a lot of them are being built on what we call slabs. So what I mean by that is the builder will come out, he may or may not bury some pipes, may or may not bury some wires, but then there's going to be this concrete slab poured and it'll lay out smooth, and that's going to be usually the actual floor of the house. The reason why that's somewhat helpful is it turns out the surface of the earth obviously changes temperature, but if you go down a small distance, you'll find that that's a rather constant temperature all the way from there for a long time. So that acts as a heat reservoir in the sense that no matter how much heat you're going to allow to escape your house into the floor, it's going to go into the earth where the earth can completely absorb that heat without changing temperatures. That's what a heat reservoir is. It can either add, you can add a large amount of energy to it, or you can take a large amount of energy away from it and it still doesn't change temperature. That's what a heat reservoir is. And you can tell that what one person considers a heat reservoir for one problem might very well not be a heat reservoir for another problem, because the magnitudes of the heat that they're putting into it could be big. So for instance, you might think, okay, well, a swimming pool compared to a toddler body heat, the swimming pool is a heat reservoir because you can put the baby in there and the baby's just going to slowly lose body temperature to warming up the water, but the water's not actually going to warm up at all because it's, several tens of thousands of gallons, or at least several thousand gallons, and the specific heat of water is so high, so the temperature wouldn't change. Now, if you instead decide you're going to, put, let's say, 100 people in that same pool, then you might actually be approaching where they're going to affect the temperature of it, and that pool is no longer a heat reservoir. Does that make sense? So this is a part of the universe where delta T is approximately equal to 0. Okay. There's another process, and these two are somewhat related and almost identical. A quasi-static process is a very slow process through an infinity of equilibrium states. It turns out, for instance, things like pressure, that's not really well defined unless you happen to have an equilibrium established. When it's not an equilibrium, it's not exactly obvious exactly what the pressure means. So I just had to write this a little better so the EQ stands up as a separate word. So just remember that word is equilibrium. The reversible process is essentially the same thing. And the main part, though, that may slightly be different, most of us consider it sort of the same as quasi-static, but in principle, you could go one way or exactly the opposite direction. And if you went back exactly the opposite direction and ended up in the same initial state you had, then that's also reversible. Okay. So it's like quasi-static plus either direction can be used or can be followed. The key point, though, with that either direction followed is, like I said, if you actually go the opposite direction that you originally were going in, then you are going in the reverse. And what makes it reversible is it'll go back to that same initial state. Whereas sometimes you can go one way, and when you go back, it's not at the same state. Okay. So that's what differentiates that. Adiabatic means no heat transferred between system and the universe. In other words, the surroundings. Okay. So no heat's transferred in an adiabatic process. You probably can really guess isovolumetric means constant volume. Isobaric, you can probably see as constant pressure. Well, let's change that. I have to put an A there for some reason. Work is going to turn out to be work equals the integral of f dot dr, but f is also given by pressure times area, and then dr could be dl, so that you see the integral of p dv, because obviously the pressure is the force applied to an area A perpendicular to that area surface A. The force actually causes you to move perpendicular to that surface A, so you automatically trace out sort of a cylinder, and that cylinder has a volume A times dl, so we call that dv. So this is just a new way of writing the work in terms of typical gas scenarios. In other words, a pressure and a volume for a gas. Now, free expansion is essentially, it is a expansion into a vacuum, meaning the pressure is equal to 0 when it expands. So you can imagine two containers connected by a pipe with a valve on it. One container you connect to a vacuum pump and you suck all the air and all the molecules out of it, and the other one you fill with whatever gas you're studying, and then you close off both of them, and you can then open the valve, and the gas in the left one, or in the one that's full, will flow into the one to the right, which has no pressure. And in fact, it shouldn't cause any change in temperature or anything. But what we find is that it actually does do just a little bit in actual experiments, that it actually does change temperature a little bit and stuff like that. But in general, that could be a result of our imperfect vacuum, because we can't get a perfect vacuum, but it might just be a fundamental law of nature that a free expansion does actually require other variables to change. So does everybody have some understanding of what those terms mean now? So we can always use, because gases behave like ideal gases, we can sort of use ideal gases to help us better understand the universe. So for instance, if you did a pressure versus volume graph like this, you could have an isothermal process go from, let's say, A to B, and that isothermal process might be like this. And you could also have, for instance, something go from here to here, and that too could be an isothermal process. And in this case, it's from A prime to B prime, and it too is isothermal. And this would be, let's say, at T equals T1, and this one would be at T equals T2. But I think you can convince yourself that T2 has to in fact be smaller than T1. And this is what I talked about, how you can use the ideal gas law to reach that conclusion. You see PV is equal to nRT is the ideal gas law. And if you put V on the other side, you get nRT over V. Now, if you say P1 is equal to nRT1 over V1, and you'll see P2 is nRT2 over V2. If T2 is if P2 is greater than P1, as you can see in the case, did I write that right? Yeah, I did write that right. So as you can see, in the case from A to B, that pressure was higher for each volume. Therefore, that corresponds to a higher temperature because that's all there is to make it higher. The N is fixed at the number of moles and the R is the gas constant. So that's sort of your proof that the higher isotherm is a higher temperature than the other one. Okay. We can also remember that for an ideal monatomic gas, E internal turns out to be 3/2 N times R times T. So so that tells you that delta E internal is equal to 3/2 N R delta T. So you can see, at least for an ideal monatomic gas, the only thing that allows E to change, the internal energy change, is a change in temperature, because it literally, that formula only depends on temperature. Again, that's an ideal gas, so and it's monatomic. It turns out if we get rid of the monatomic, you can have, instead of 3/2, you might have 5/2 for one temperature range, and for another temperature range, you might have 7/2. So some other forms might also be delta E internal is equal to 5/2 N R T, or 7/2 N R T. And your book talks about that a little bit. Okay. But all three of these are really for ideal gases, but because they work so well, it's also somewhat true even for non-ideal gases that they will act very much like this. Okay. So that's sort of a paradigm we can use. We also know, for instance, that since delta E, so the first law, whoa, everything just moved on me there. So with the first law, delta E internal is equal to Q minus W. If it's truly isothermal, then delta T equals 0, which suggests delta E internal is equal to 0, which means all of the heat goes to work. So that's one of the ramifications of isothermal, especially dealing with the ideal gas. As I said, the ideal gas is an ideal gas, but it's only useful because it mimics the behavior of real gases. So at least in some sense, you expect this world to be somewhat right, where work equals the actual heat added for any particular gas if it's an isothermal process. Does that make sense? Everybody understand that? A little bit, maybe. Okay. So that seems like that's somewhat of a yeah. So I'm going to go with that. Anybody have any questions before we go on? All right, now let's consider an adiabatic process. So that was isothermal. Now we're going to consider adiabatic. Adiabatic literally means Q is equal to 0. So the first law of thermodynamics, delta E internal is equal to Q minus W, implies delta E internal is equal to the negative of the work done. And this, of course, is for an adiabatic process. Now, this part might not be quite as obvious, but let's look at a graph real quick again. So if we take a pressure versus volume graph, there's the volume, there's the pressure, and we start from A, it turns out that there's an isotherm that connects A to B, and this is isothermal. Whoa. Now, you could also leave A and end up somewhat below B, and in that case, this would be an adiabat. And in fact, when you're talking about a process on a graph, you could call this not isothermal, which is what it is, but you could call this actual graph an isotherm. Whoa, I don't know if I used the right color pen there. So that little blue line is called an isotherm, just like that little red line is called an adiabat. Basically what you're looking at is for an isothermal, you have delta E internal is equal to 0, which means the Q is equal to W. But for an adiabatic process, it's Q minus W, but Q is equal to 0. So delta E internal is actually equal to the negative of the work done. And that is for the adiabatic process. Now, you can look at it that way. And what I'm trying to do is convince you that, in fact, the adiabat does leave A, but consistently has a lower pressure. Okay. Well, if you're talking about an ideal gas has PV equals nRT, right? So if you're solving for P in terms of V, you get nRT over V. But in the case of, and that's isothermal, by the way. And in the case of P equals nRT over V for adiabatic, in that case, the temperature can change. And what you're doing is you're actually going from a high pressure to a low pressure, and the volume's actually expanding. When a volume expands and is allowed to expand, it's actually going to cool down. So, since this is not isothermal, I hate that. Since this is not isothermal, T lowers due to the expansion. Which means P adiabatic is lower than P isothermal. Does that make sense now? So I can go ahead and knock off this line and include that graph there. That's pretty helpful. We've got all that now. There's ways that things can be adiabatic and isothermal. If it's isothermal, that's a little harder to do. It's more like you look at an experiment and it's underway and the temperature never changed. So you say, oh, wow, that was an isothermal process. Woohoo. it's a lot harder to control matter so that it won't change its temperature. So obviously that's a difficult thing to do, unless you're dealing with a heat reservoir, and then by default the temperature is not going to change. In the adiabatic process, however, you can actually create something like a calorimeter, which we showed you last time. And in that case, you're not actually allowing heat to enter the system or to exit the system. So that's one you can control pretty well. So we know that in the adiabatic process, that all the internal energy is changing as a result of the negative of the work done by the system. Okay, so that again reminds us that work done by the system is what we call positive. Now, when we're talking about these types of processes, we also need to know, well, how do you make isothermal or adiabatic? Well, I told you adiabatic can be done by just using like a calorimeter or a good cooler system. Isothermal or adiabatic both can happen by processes that happen very quickly. So your book mentions, for instance, that a diesel engine might actually compress the gas. Like, let's imagine, for instance, you had a 8-liter V8. So if you had an 8-liter V8 diesel, okay, then that means each piston has a difference in volume. When the piston is all the way down to when it's all the way up, it has a difference in volume of 1 liter. So in the case of a diesel engine, that compression can be huge. Like you can go from 1 liter down to a 1/15 of a liter. That's a really high compression diesel engine. And if it does that really rapidly, the process that happens to make energy flow into or out of the piston, or that makes temperature change, are sort of the same. Remember, the atoms or molecules are vibrating, are moving, and their tangential, or excuse me, their linear motion in the x direction, in the y direction, and z direction, that kinetic energy from each of those three add up to give you the total kinetic energy on average of the molecules. So in order to try to change the temperature, what you have to do is take the atoms or molecules, say in the gas that you just compressed, and they've got to interact with the atoms and molecules in the walls of the piston, and do so in such a way that they not only increase the kinetic energy of those atoms or molecules in the wall of the cylinder, but throughout, such that the whole average kinetic energy of all of the molecules increase. Once that's done, then energy has been officially transferred from the piston to the surroundings. Similarly, the same thing has to happen if you're trying to change the temperature. The individual atoms and molecules in the compressed piston have to bump against the atoms and molecules of the surroundings until, again, that average changes. So a thermal process where the temperature changes, and a non-adiabatic process where heat escapes, actually takes a little bit of time. So in the case of a diesel engine, compressing by a ratio of like 1:15, that can often be isothermal and adiabatic because it happens so quickly. Okay, so that's the main thing I'm trying to get across to you. A regular car engine, by the way, they're more likely to only have a compression fraction or compression ratio of a couple, like 2 or maybe 3 or something like that. But the diesel has such a high compression that they actually ignite the gas and cause the explosion without a spark plug. That's the difference. One of the differences between a diesel and a gas engine. A diesel engine has no spark plugs because it doesn't need it. It literally makes the temperature, makes the pressure change such a huge amount, by such a huge amount, that it increases the temperature enough to cause the explosion all by itself. Whereas in a regular gas engine, you have to have that little gap between the nub on the spark plug and the little L shape at the end of the spark plugs. Like, here's the little gap, and electricity comes through there, and it's like a little lightning bolt striking from one to the other. That is basically fire moving along a path and therefore causes an explosion. All right. we're now at 6:25. I think this would be a good time for me to give you your 10-minute break. So everybody take your 10-minute break. Be back at 6:36. And I'm here if anybody has any questions. So 6:36, be back. So wait a couple more minutes. Got a couple more minutes. Still got about 4 more minutes. Anybody have any questions for me?
I have a question,
Yes.
but it's very random. So
Mhm.
you might take it however way you want. But do you drive a Ford F-150 XL?
I do not. I just bought
Dang.
a Ford F-250 or 350, but
Oh,
do not drive that. Why, you thought you saw me
I
somewhere?
was I was in Virginia Beach like a few mornings ago or something, and I saw this guy drive by, bald head, Ford,
Handsome, awesome looking. Yeah.
something like that. And I was like, is that younger? There's no way.
Yeah, sadly, there's a bunch of bald people like me all around the world.
I only know a handful, so when I see them, I'm like, that's gotta be
That's
them.
gotta be it. Yeah, I get you.
And plus Virginia Beach, like I know you teach there, right?
Yes. Yeah. So I'm
So
always going that route.
I definitely was like, that's gotta be you.
Clearly, there can't be two like that.
Yeah.
Not me this time, and I haven't ridden in one lately. I do have friends that have them, but I haven't ridden in one lately, so most likely it was
Oh,
not
good.
me.
Anyway,
But I did buy a
I
red
see.
250 off Centerville Turnpike the other day. So
All right, cool.
I think that
I'll
was
keep an eye out.
yeah. I think I bought that. I think I bought that Saturday. Yeah. So that happened, anyways.
Nice.
Yeah, I was very
You
excited
trying to
about
get me one too?
Yeah, I wanted to have a truck that I could use to tow a camper when I ever get one, and I bought a Dodge, but the towing capacity on that's a little lower
Hmm,
because it's a 1500. So I found another
gotcha.
one that's really really old, a 2003, and got that. So
Mm,
I'm very excited about the whole process.
nice, yeah. Getting a truck is always fun.
Yeah, yeah, yeah. I like it. All right, looks like we're about ready to go then. Anybody have any questions before we get fired back up? Okay, so I wanted to talk about a couple other things. We've done adiabats, we've done isothermal. Now I need to do isovolumic or isovolumetric and isochoric. So I've drawn a couple PV diagrams to help us with that. Let me go ahead and share my screen again. Waiting. Any minute now. We're on our way. All right, we're here. Okay, cool. So I had made this window small and I still can't figure out again how to do it. But anyways, here we are. What is that? Dang it. Nah, that's good enough. Okay. So first off, if we have a plot of pressure versus volume, we can sort of make sense of isobars and isovolumetric processes by drawing them on the pressure versus volume graph. I should point out that on these graphs, it's impossible to have a point on a graph unless that state is in equilibrium. Again, a lot of these terms aren't really defined well, pressure definitely being one of them, unless it's in equilibrium. So if I wanted to talk about isobaric process, what I would have is a process that goes from A to say B like this. And that's isobaric. And this is called an isobar. So, and again, it's a process. In this case, since I labeled it A and B, it's probably that I'm going from A to B. It doesn't always have to be that way. In fact, they should give you arrows or tell you explicitly what way it is. Now, in the case of isovolumetric, I think y'all can probably guess what this one's going to look like. Whoa, this is going to look like I'm going to erase everything because my stupid thing keeps jumping to erasing. And I'm going to say that's A. And let's say that's B. And maybe I'll do it in red this time to let it stand out. And again, I'm going that. This is an isovolumetric process or an isochore, if I remember correctly. I think that's the word for it. I'll put quotation marks around it because I may be misremembered, but if I remember correctly, I think isochoric is another word for isovolumetric. It could be isobaric, but either way, I'm just looking for a word that's shorter than isovolumetric because it's got a ton of syllables. Now, the other thing that happens with isobaric is that work, which equals the integral of P dV, since the pressure is a constant, it just becomes the integral of P, or P times the integral of dV, which would be P times delta V. So this is isobaric, and this is an isobaric result. And of course, that doesn't say anything about temperature, so the delta E is still able to change. It doesn't say anything about heat escaping, so the Q is still not zero, and it does allow the volume to change. And since the volume can change, that means it can actually do work because work is the integral of PdV. In this case, the isovolumetric case, which I'll circle with black lines just to let it stand out from the other one, work. Well, actually, I'll go ahead and do, let's do blue again. Work is equal to the integral of P dV, but dV is equal to 0, so you get 0 there. And that is, in fact, another result of volumetric process. So we also get that delta E internal is just equal to Q. So that's another result for isovolumetric processes. Any questions on that? Now, there's some ramifications that come from this. Like when we talk about adiabats, your book goes through a long derivation, which I think I've done it before on my YouTube channel, so it should be up there. I know I usually do it in class, but I'm trying to do a little bit fewer derivations in class so I can help y'all better with the actual problems, whether it be solving more difficult problems or talking more about the concepts behind the problems. That's what I'm trying to do here. So if we happen to luck out and use, assume we have an ideal gas, then the integral of PdV can work quite well. And you can get P is equal to nRT over V. And if it's an isothermal process like we had above, I can do this. Let's do, I'll do blue again. So work is equal to integral of PdV, which equals the integral of nRT over V dV, which equals nRT times the integral of dV over V, which ultimately equals nRT times the natural log V2 over V1. So that is yet another ramification of isothermal process, that work is equal to nRT times the ln of the final volume over the initial volume. So all of these things are actually consistent with isotherms. I already did the stuff for adiabats up top. In fact, I probably would not have hurt if I'd stuck a black line between them. So I'll sort of do that now just to keep it straight, even though the diagram immediately below had an adiabat and an isothermal there. All right. So we've sort of covered all those processes and what they do. Now I want to solve some more problems. So I'll start off with this one. In which case is W the greatest? So what we're looking for is W, the work done. And the work done, remember, let's say solution. The work done is equal to the integral of P dV. So what we're actually doing in both cases is we're imagining a Riemann sum of these infinitesimal things right here, where the height is in fact P and the width is in fact dV. So what you see is that you're in fact getting the area under the curve. So the area under the curve is what that is. So we can now definitively say which one is more work, the isotherm or the adiabat.
Yeah, isotherm.
Exactly. So the isothermal, actually I should probably do process and so the isothermal process caused more work to be done. So that's our answer there. Any questions on that? Hopefully that makes some sense to you. And the main reason you see that, of course, is you're going from A to B or A to C. In both cases, you're starting off with the same volume, VA for the A point, and VB, which is also equal to VC for the away point. But what you see is the pressure is consistently higher on the isotherm than it is on the adiabat. That's why you consistently get more work as the area under the curve. Now, if we look at the next diagram, it says, is the work done in going from A to D to B greater than, less than, or equal to the work done in the isothermal process, which of course the isothermal process is this one. Anybody want to take a guess on that one?
What was the question?
Which work is the work done and going from A to D to B? In other words, that vertical line down, then the horizontal line. Is that work greater than, less than, or equal to the work in going from A to B along the isotherm?
Like each of them combined?
No, which one's greater, the work under the AB curve or the work under the ADB curve? Does that help you understand it more?
Would it be equal?
Remember, it's still the same work equals the integral of PdV. And notice the P is consistently higher on the isothermal process. Y'all see that? So if you're wanting to look at the, let's do my little Riemann sum here. This is P ADB, and this is DV. Whereas when I do this one, let's say here, this is P isothermal, and this is DV. So you see P isothermal is greater than P ADB. So work in isothermal is greater than work in ADB. Okay. Does that make sense now, Nora, or anybody else for that matter?
Yeah, it does. I was looking at it completely wrong. I thought you meant inside of the
Gotcha.
triangle, but if it's just under the curve, then it would be from A to B still.
Well, it's good that you mentioned that, because if I take that same diagram and let's say I did work going from A to B, that means I'm going from left to right. Okay. That would actually be a positive amount of work. And then on the way back, I would go from B to D and then from D to A along those two lines, the first one being horizontal, the second one being vertical. Now, going through that whole cyclic process, then the area inside is actually the work done.
Over the entire cycle, but within the two processes, it's different.
Yeah, it's just under for a given process, but for a cycle, it's the area inside.
Gotcha.
So
thank you.
No problem. Cyclic process. That's great. Cyclic processes implies work equals area inside. Now that cyclic process is actually important. It turns out that's what makes a heat engine, because you actually go from some point A to the equivalent state, and then you can repeat it over and over again. So I wanted to go ahead and mention that, because that's part of what happens in chapter 20. Now, with that being said, let's look at this next part. So let's see. We have an ideal gas that's compressed slowly at constant pressure of 2 atmospheres from 10 liters to 2 liters. So I'm talking about in this bottom diagram going from B to D. Okay. In that process, heat actually flows out. And of course, that also causes the temperature to drop. Normally when you compress something, obviously that would make the temperature go up, because the volume is actually well, it could make it go up. Let's put it that way. But in this case, the T is actually going to drop and heat will flow out of the system. Then heat is added to the gas from D to A. And in that process, it's going to be done so at constant volume. So in other words, we stop the cylinder, the piston on top of the cylinder, and don't allow it to move anymore. And we start adding heat into it, and that causes the pressure to go up, but without expansion. So it goes from D to A. Obviously, this means that TA is equal to TB. And of course, TB is the temperature that it has right here. And TA is the temperature it has right there. This is some other, D is on some other isotherm. So that would be temperature D right there. Okay. What we're asking though is heat is then added to the gas by holding the volume constant, and the pressure and temperature are allowed to rise along the line D to A until the temperature reaches its original value. What we want to know is what is the total work done by the gas in the process. So I want to know work total from B to D to A. That's a question mark, and that's part A. And then part B, I want to know the total heat flow into the gas. So Q total equals question mark, because it says into the gas. So we can now work through this process quite easily. Let me do it with this. I'm going to say solution. So first off, I'm going to talk about part A. And part A, the work, notice that's actually at constant pressure. So that actually equals P times delta V. So the work is actually equal to, in this case, it's going to be 2 atmospheres, which is 2 times 1.013 times 10 to the 5th pascals times final minus initial would be 2.0 minus 10.0 liters. Well, that's not going to give me units of joules, so I've got to actually allow that to be expressed in cubic meters. And to do that, I know that 1,000 liters is equal to 1 cubic meter. So I've got to actually divide by 1,000. And that would be liters per cubic meter. So that's my conversion. You can see that the work is going to be negative. I can in fact calculate it as 2 times 1.013 e to the 5th times 2 minus 10, which ultimately gives me 2 sig figs, and then I'm going to divide that by 1,000. And I don't know why that, oh, I see. So 2 times 1.013 e to the 5th times parentheses 2 minus 10 divided by 1,000. That gives me negative 1,620.8 joules. Negative 1,620.8 joules is the work done on that part. Now, because I did 2 minus 10, they're only known in the 1 decimal place. So that ended up giving me 8.0, which is only 2 sig figs. So technically, I'm only allowed to have the 1,600. So I should write that as 1.6 times 10 to the 3rd, but it doesn't matter too much. That's the answer for part A. Any questions on that? Now, notice this is actually a negative, and that means work is done on the system, but that's exactly what we expected because the gas is being compressed. It used to be 10 liters and it's forced down to 2 liters. So that's the atmosphere doing work on the gas. Now for part B, they want to know the total heat done, or excuse me, the total heat added. But what you'll realize in going from B to A, the total internal energy has to not change. So what I mean by that is with regards to part B, delta E internal from B to A is actually equal to 0 because TA is equal to TB. Because they're on an isotherm, right? So what that means is 0 is equal to Q minus W. And that means that, in fact, Q is equal to W, which equals, of course, negative 1.6 times 10 to the 3 joules. Any questions on that? All right, now your book does examples like these, and then it has these little exercises that are in gray boxes. Those are great, and you can actually find the answers. If I remember correctly, I think the answers are at the end of the chapter. So you can look for the individual exercise ends and check those as you go. That's another little check that helps you. And they're usually quick and dirty calculations, so you can do them with almost often without a calculator. So that's the kind of thing that you should do in real time. Now let's consider another problem. And it says, in an engine, in an engine, 0.50 moles of an ideal monatomic gas in a cylinder expands rapidly and adiabatically. Okay, rapidly and adiabatically. There's supposed to be 2 L's there. Actually, let me just go ahead and erase that word and write it on the next line since I ain't gonna have room. And adiabatically. In the process, the temperature drops from 1200 Kelvin to let's say 390 Kelvin. How much work does the gas do? So that's the question. So an engine, I'm going to say this is a solution. So a heat engine is running basically on 0.5 moles of an ideal gas, which is in a cylinder, and that gas rapidly expands. And it does so adiabatically, specifically because, like I said, when something happens so fast, it's really hard for heat to escape and stuff of that sort. So in the process, the temperature drops from 1200 to 390 Kelvin, and they want to know how much work is done. What we know is delta E internal is equal to E internal final minus E internal initial, which is, of course, 3/2 N times R times T final minus T initial. So delta E internal, we can work out. And then once we know delta E internal, we can use it and the fact that it's adiabatic to find out the work done, because delta E internal is equal to Q minus W. So in this case, it's adiabatic, so that Q is 0. So delta E internal is actually the negative of the work done, or specifically work is equal to the negative delta E internal. So I'll put a negative here, and I'm going to do 3/2 0.50 moles times 8.314 joules per mole Kelvin times T final, which is 390 K minus 1200 K. Okay, so notice that 390 minus the 1200 is going to actually give you a negative number, so that'll ultimately make the work positive. So I'll say 1.5, that's 3/2, times 0.5 times, let's say, negative 8.314. In other words, I'm just trying to put the negative in there somewhere. And now I'm going to say times parentheses 390 minus 1200, close parentheses, and I get 5,000. Now looking at this, it looks like I only have 2 sig figs because of the moles. So I'm going to say that's 5,051 joules. And I'm going to underline these last 2 digits. And that should be the actual work done. Any questions on that? That's pretty straightforward, right? Easy peasy. So another problem. No questions on that one, right? So what I'm going to say now is, what is the change in E internal of a 2.00 liter? Technically, I'm supposed to write a dash with that. 2.00 liter. Actually, no, I shouldn't. And I shouldn't have called that an A either. So I'm going to say, what is the change in internal energy of 2.00 liters of water at, dang it, do it again, at 100.0 degrees Celsius when it boils fully boils away into a gas, which results in 1,600, let's say 1,600 liters of steam at 100.0 degrees Celsius. Assume this is done. Whoa. At P equals 1.00 atmospheres. Okay. So here's our solution. If you notice, what we have here is they're wanting to know a change in internal energy. What we know is the change in internal energy, delta E internal, is equal to Q minus W. We know Q is the heat added that actually causes it to change state. Anybody remember what that heat is called?
Latent heat or specific heat or
latent
one of
heat.
them?
Latent heat's the right one. That's how you change state. The specific heat's how you change temperature. And in this case, it's actually the latent heat of vaporization because it's going from a liquid to vapor. Okay. So in this case, it's M times LV. And the work done, since it's done at constant pressure, is just P times delta V. So we've got everything we really need. All I have to do is say delta E internal is equal to M times L. Now, 2 liters of water actually has a mass of 2 kilograms. So that'd be 2.00 kilograms times the latent heat of vaporization for water, which is 22.6. I'm looking that up from a table. Actually, I remember it off the top of my head. But in general, that's something that we have to give you to solve the problem, or we have to give you access to the table. There's literally a table in your book that has this figure, and that's joules per kilogram. So that's the ml. Of course, you also got to remember that heat has to be added to the steam so that the individual molecules can move so fast that they can break their bonds that hold, a particular molecule near the same 4 or 5 molecules for, a long time on the microscopic scale. Then I'm going to say, darn it, do it again. Then I'm going to say minus the work done, which is 1.013 times 10 to the 5th pascals. That's the pressure. And then the volume is initially only 2 liters, but finally it turns out to be 1,600 liters. So that'd be 1,600 liters minus 2.00 liters. And then, of course, if I multiply liters times pascals, that does not give me the right unit. So I've got to actually convert this by dividing by 1,000 liters per cubic meter. So there's my conversion factor. In this case, I get 45.2 times 10 to the 5th joules minus 1.013 e to the 5th pascals times parentheses 1,600 minus 2, and then I'm dividing all that by 1,000, and that gives me 1.619 times 10 to the 5th. All that will come out to be joules. So ultimately, I get that the change in internal energy is is 4.358 times 10 to the 6 joules. Now we had 3 sig figs for the first number, so that would have been 1 whole number and 2 decimals in 10 to the 6th. And then the other one we had, again, you can assume, yeah, you can assume at least 4 sig figs for that one. So we're actually limited by this, which means this digit right here, the 8, is not a sig fig. So our ultimate answer is about 4.36 times 10 to the 6 joules. Any questions on that? All right. After problems like that, your book talks a little bit about free expansion. In fact, they end up telling us that experimentally, the free expansion has been used to determine if the internal energy of real gases depends only on T. The experiments are very difficult to do accurately, but it has been found that the temperature of a real gas drops very slightly in a free expansion. Thus, the internal energy of real gases does depend a little on pressure or volume as well as temperature. So there's something else going on in there. We don't exactly know, but what we do know is that a free expansion does take and causes it to cool down just a little bit. And that's sort of not unlike the coldness of hairspray or deodorant when it comes from a high pressure system like your the can to the air that hits your arm. The can will actually cool off as well. Any questions on that? All right, so the next part that we're going to cover is in fact let's see is in fact the specific heat in a different way. So specific heat we're talking about now is specific heat, molar specific heat. So instead of calories per kilogram degree Celsius or joules per kilogram degree Celsius, we're going to talk about calories or joules per mole degree Celsius. And that's not as difficult as you might think, but it turns out that at least when you're dealing with gases, it makes your life a lot easier, and it makes it where you can determine a lot of stuff. There's a whole table on it in your book in section 19.8 where it has the specific heats in kilocalories per kilogram per Kelvin, both for constant volume and constant pressure. And it has them also in molar values, and it has Cp minus Cv, and it has a quantity called gamma, which is the ratio of Cp divided by Cv. But it has it for monatomic gases, diatomic gases, and triatomic gases, and polyatomic gases. And you see that surprisingly, the Cp minus Cv is roughly 2. And that's in the molar value. And the ratio is of Cp over Cv is like 1.67, 1.4, 1.3, somewhere along there. But all that comes out a lot easier when you're working at it in terms of gases. So what we're going to do is I'll erase this page for starters. Clear page. Nope, I did not mean to do that. I meant to erase page. And I'm also going to do that to this one back here because that wasn't supposed to be there either. Okay, so I got that. Now, with this new idea, we know instead of Q equals MC delta T, we now have Q is equal to N CV delta T, and Q is equal to NCP delta T. So remember, when you actually are talking about C sub V and C sub P, this means constant volume, and this means constant pressure. Which makes a big difference. You might not see it immediately, but in general, we could, for instance, talk about Q equals CV delta T, and Q is equal to MCP delta T with lowercase c's, okay? And that would be fine. The main thing is that the ratio, or excuse me, the way you go about calculating them is this. Basically, CV, the molar specific heat at constant volume, is the molecular weight times the specific heat at constant volume. And CP, the molar specific heat at constant pressure, is in fact equal to the molecular weight times lowercase cp. So these are some other equations we use. Again, I would normally go through the full derivation here, but I don't think we need it that badly. I think it's more important that you see how we use them and that you hear me explain it. Basically, what you realize is that the specific heat is about changing the temperature. And if you have specific heat at a constant volume versus a constant pressure, things happen a little differently. So for instance, we have delta E internal is equal to Q minus W. So if V equals a constant, then Q is equal to delta E internal, which we said, at least for a monatomic ideal gas, is only dependent on temperature. So every calorie that you put in at constant volume goes to changing the temperature. So every joule or calorie added to a gas at constant V goes to increasing the temperature. And I'll say that's roughly because I'm using the idea of an ideal monatomic gas to reach that conclusion. As we know, the the internal energy can actually depend on other things in real gases, but largely it behaves like an ideal gas. So that's a good first order approximation at least. So every little calorie or joule that you put into a gas at constant volume automatically goes to increasing the temperature. So it should take less energy to go to change the temperature. So this implies that CV is in fact going to be less than CP, because at constant pressure, you just get work equals P times delta V, but work can be done. So some of the heat's being wasted in expanding the gas, whereas the other part is just for the temperature. So we do expect CP to be bigger than CV. And from that, again, your book does the derivation. It's pretty straightforward. I think you can understand it pretty easily. But what we ultimately come up with is CP minus CV, which again shows that CP should be larger. That CP minus CV is in fact equal to R. So that's another big result that's helpful for us. And not only that, you can carry it a little farther and use the fact that the internal energy is capital N, the number of molecules or atoms, times 1/2 mv squared on average, that's equal to 3/2 nRT, and set all that equal to N CV delta T, because in the case of CV, V is constant volume. So all the energy goes into changing the temperature. None of it goes to work. So you can ultimately get that 3/2 nRT, or nR delta T, is equal to N C sub V times delta T, which makes you think, oh, CV must be 3/2 R. And that's exactly right. Actually, let me write that in black now. So that's another valuable expression we have. And of course, you can plug that into the previous equation. And if you pull it to the other side, you'd see that 2/2 R plus 3/2 R is 5/2 R. So now we've got CP. Oops, again, I need to write it in black. CP is equal to 5/2 R. So now we've got a bunch of things we can use. That's wonderful. And in fact, there's another process you can go through solving a fairly simple differential equation. It involves some natural logs, stuff of that sort, but it's not that big a deal. I already talked to you about the internal energy having different degrees of freedom for the higher temperatures. So that's what's covered in section 19-8.2 or -8-2. But now I need to go to the part about the adiabatic expansion. So if we assume an adiabatic expansion, and I don't know how I got where I did, so let's see, assuming an adiabatic expansion, then we can show that basically P1 V1 to the gamma power is equal to P2 V2 to the gamma power, where gamma is defined to be CP over CV. Okay, so this is a really, really big deal. This is another thing we can use in addition to the ideal gas law. What it really says is P times V raised to the gamma power is a constant, as long as you're not allowing N to change. In other words, you got a closed container or something like that. So this is a really big deal. It can allow us to solve problems that we couldn't do before. So let's go ahead and put that to the test and see what can happen. So I'm going to try to change pages, and let's say an ideal monatomic gas is compressed at a C diagram where P sub A is equal to 100 kilopascals, V sub A is equal to 1.00 cubic meters, and T sub A equals 300 Kelvin. The gas is compressed adiabatically first. Darn it. First to state B. Again, see the diagram where PB is equal to 200 kilopascals. Then the gas is further compressed to point C, or let's say just to C, where where VC is equal to 0.5 meters cubed. Okay. In an isothermal. Actually, that turned out really ugly. Let me rewrite that. In an isothermal process. A, what is VB? And B, what is the total work done? W. Okay. So that's our problem. I need to go ahead and draw the diagram. So let me give you the diagram that I'm referring to. So what I have here is a pressure versus volume graph. The volume is in cubic meters and the pressure is in kilopascals, like so. I have 0.50 cubic meters is right here. That's what I'm calling point C. 200 kilopascals is right here. And that's point B. And then 100 kilopascals is right here, and that's point A. And that corresponds to 1.00. Now, what I'm doing is going like this, and then like this. And of course, this part is an isotherm. And this part is an adiabat. So solution. So when we go to do this, the first part we know is in fact a isothermal process, and then the other part, or excuse me, the first part going from A to B is an adiabatic process. So we have that new equation we can use, that P times V to the gamma power is equal to P times V to the gamma power. So we can work that out. We also can realize that gamma, which is CP over CV, is supposed to be roughly 5/2. Again, this is something you can look up, over 3/2. Again, from the table, that ends up becoming 5/3, which you should recognize as 1.666 or something like that. 5/3. Yeah, 3 goes into 5 one time, and then that's 2 left over, and then that's 2/3. So this should be 1.667, maybe something like that. So we have gamma, and for part A, PA VA to the gamma is equal to PB VB to the gamma. I did this the other day in my class, and I used natural logarithms to do it, and I ended up making a mistake, but I later found out that it worked fine. It was just a mistake that I had copied one of the fractions upside down. So I ended up taking like the natural log of 2 when I was supposed to take the natural log of -2, or excuse me, of 1/2. And that should have been -0.693 instead of +693. And that's why it was wrong. This time I'm just going to do it without the natural logs. The first part I'm trying to solve is VB. So I can say that VB to the gamma power is equal to PA over PB times V to the V to the gamma power. That's VA to the gamma power. Now I can raise both sides to the 1/gamma power. And when I raise VB to the gamma power to the 1/gamma power, that's just going to give me VB, which is what I want. The other side is going to give me PA over PB to the 1/gamma power. And the VA raised to the gamma power, but then raised to the 1/gamma power is just VA. So what I'm going to do is I'm going to say PA, which is 200. And it's technically kilopascals, but I think you can see that not only do the kilopascals cancel out, but the 0 cancel out as well. Actually, I got to do that. I almost did the same thing again. Remember, I just told you about turning my fraction upside down. So PA is supposed to be 100. And PB is supposed to be 200 kilopascals, and that's raised to the 1/gamma power, and then I'm multiplying that by 1.00 cubic meters, which is the volume of A. So finally, I get that VB is equal to 0.5, and I'm going to raise that to the 1/gamma power. What we found was 1/gamma, or excuse me, gamma was 5/3. So 1/gamma should be 3/5. So I'm just going to say raise 0.5 to the 3/5 power. And that gives me 0.6597. And then I multiply that by 1, which is easy peasy. So this gives me essentially 0.6. Oops, I should probably write it in the same color I was doing. 0.6598 cubic meters. And technically, we can assume we had 3 sig figs for the 100, the 200, and the 1, in which case this guy right there is the only non-significant figure. But that's the answer to part A. We've got that done. Now I want to know what's the total work done. Well, the total work done in this process is the work done from A to B plus the work done from B to C. In A to B, we actually just have something where the pressure changes and the volume changes. But we are told it's an ideal monatomic gas, so we can actually use the ideal gas law. So for part B, I say work from A to B is equal to the integral of, let's see, work done from A to B. Let me think here. Oh, since we're actually calculating the work done on the gas, or excuse me, by the gas instead of the work done on the gas, I need to include a negative. So I'm going to say it's the negative integral from A to B of PdV, but it's an ideal gas and it's an adiabatic process. So I can use both things. I'm first going to use the adiabatic process. So I can say that the pressure at any particular time is given by this. So let me write this over on the side. I'll say P times V to the gamma is equal to, we'll just use the values we were originally given. So that's PA VA to the gamma like that. So we can actually say that P is equal to VA over V, all that to the gamma power times PA. So when I go to do that, I can actually say, back to my blue, I get negative integral PA VA to the gamma. Dang it. Dang it. Stop it. It keeps changing on me. PA VA to the gamma times the integral from VA to VB of V, or I should say dV over V to the negative gamma. Because that's basically what V is down here in the bottom. It's V to the negative gamma. So this actually gives me work AB is actually equal to negative PAVA to the gamma power to the 5/3 power times. Now, initially what's going on here is we've got to realize what gamma is. Gamma is an actual number. So when I try to integrate V to the negative gamma, I end up getting basically negative gamma plus 1. Yeah, I think, yeah. To be divided by, so this is negative gamma plus 1. And then the V actually comes out to the 1 minus gamma power because I'm actually adding 1 to it to integrate. So this becomes VB to the 1 minus gamma minus VA to the 1 minus gamma. That's the whole thing here. So now I can write negative, let's say, I think I got everything here. Yes, that's right. So negative PA, we said PA was 100 kilopascals. Times VA was, in fact, I think it was 1 cubic meter. And that, of course, is raised to the 5/3 power. And then if I take gamma, which is the 5/3, then I do negative 5/3 plus 1 in the bottom. That would be negative 5/3 plus 3/3 be negative 2/3, and negative 2/3 in the bottom is negative 3/2. So I'll say times negative 3/2. That takes care of that fraction right after the 5/3. And then I say VA to the negative 1/3, which again is that one. Oh, I had already done that. Sorry. And now I'm going to do VB. See, would that work? Yeah, VB we found already was 0.659 or 0.660. And I'll leave the units off there because it's just ugly at this point. This is going to be raised to the 1 minus 5/3. So it's 3/3 minus 5/3 is negative 2/3. So it'd be negative what? Darn it. Grr. Negative 2/3 power minus 0.50 also to the negative 2/3 power. And that ultimately should give me skipping some calculations just because they're ugly. That ultimately gives me positive 48 kilojoules. And that's just the work from A to B. Now the work from B to C is equal to, again, the negative integral, because again, we're calculating the work done by, not the work done on. So this is going to be the integral from B to C of PdV. But in this case, P is just nRT over V, and this is an isotherm. So it's going to be negative nRT times the natural log of VC over VB. Okay. In doing that, we have everything. Do we have VC? We don't. Yeah, we have VC was 0.5. Okay, so that all works. Now, putting in all these numbers, the N was an ideal monatomic gas. Sorry about that. We only have about 5 minutes. So let me just go ahead and write down what the final answer is. The final answer here is plus 37 kilojoules. So we can say that the work total is supposed to be the 37 kilojoules plus the 48 kilojoules, which is about 85 kilojoules. And that's the total answer for part B. Okay. This one is essentially the same as the one in your book. I don't even think I changed any numbers from it. So you should be able to look up that, see how that's done. You can see the calculations, all that good stuff. But that's essentially it. The rest of the stuff is what I consider chucker questions. So there's neat stuff like, for instance, convection, conduction, and radiation. And I've hinted at those before, but just to give you an idea, when we talk about conduction, conduction is the transfer of heat by touching. In other words, one thing's got to touch the other thing. And it turns out that the heat added, actually, let me not use that color. Let me use blue. The heat added per time is actually directly proportional to the cross-sectional area. That's the area of contact between the hot thing and the cold thing. It's also directly proportional to the difference in temperature from one side to the other, T1 minus T2. And it's also inversely proportional to the distance between them. And the constant of proportionality is K, which is called the thermal conductivity, which you can look up in your table. But this is pretty straightforward plug and chug sort of stuff. What we're talking about here is, let's imagine a heat reservoir at temperature T1, like so. it has a conductor connecting it to heat reservoir T2. In other words, the temperature of that one's T2, and T2 is actually less than T1 because heat is going to flow this way. Okay. That area is A, and this length from here to here is L. So that's what all that rigmarole means with all those symbols, is basically obviously the cross-sectional area of the conductor through which the heat has to travel. The bigger that is, the more heat can flow, just like the bigger a hallway is, the more people can walk through it. And also, the longer that hallway is, the slower the people can get through it. So similarly, the longer that conductor is, the slower they get through it. So that's one equation. I should admit, I should mention to you that L over K is the R value that we know of from building. So like when you use 2x4 walls, you have R13 insulation. When you use 2x6 walls, you have R19. And what they're doing is they're taking the L and they're absorbing the thermal conductivity, and they're doing the L divided by the R to get the thermal conductivity in R values. You can also make this into dq over dt is equal to negative K A dt over dx. Now you've got it in a form that makes it look like a gradient, which is kind of helpful. So that's a temperature gradient that you see, dt over dx. That's one thing. I already showed you the Stefan-Boltzmann law is another thing, which is supposed to be pretty straightforward. Windows, for instance, can actually save a lot more heat than you think, and that's mostly because a little wafer of air that exists on each side of the window. They realized how good that was. That's why they started making double pane windows, because then you could trap the air inside, and then you've got air as an insulator, in addition to the little wafer of air outside that can sometimes be blown away. Now, in terms of radiation, we have the Stefan-Boltzmann equation. This one already, actually, I might have just mentioned it to your to the face-to-face class, so I'm going to tell you now. Class is almost over. So what we have again is that that Q over T, which is also called the luminosity of a star, for instance, is equal to epsilon sigma A T to the fourth. And what that means is the emissivity is that little epsilon. That's a measure of how reflective versus conductive it is, or how well it gets rid of the energy. The sigma is the Stefan-Boltzmann constant, which you can look up. The A is the surface area. So, if you have a really big pot of water and you want to boil it quickly, if you put it on the small burner, it's not going to work. That's because the heat per time is directly proportional to the area. So if you use the burner that's closer to the area of the pot, you'll get a better result. For stars, of course, that's essentially 4 pi r squared. And then here's the big thing. If you double the temperature, you 16 tuple the luminosity, or the amount of heat per time. Notice heat per time is joules per second, so that should come out in watts. That's it. We're done. The questions with regards to this, these 3/2 equations are really chucker questions. You guys are free to go. I will wait for the last person to leave in case anybody has any questions. And that's it. Have a good weekend. I hope everybody did really well on your tests. I will be checking through those. I'm also going to check them for errors, because this morning I went through and did all the tests, but in the 241 class, I accidentally must have erased 3 of the problem answers. and replaced them with another one. If you just click on it in edit mode by accident, it'll actually change. So I think that's what happened when I was changing the points. I accidentally clicked on the answers. So it was grading 3 of them wrong. I don't think that happened with yours, but I will check it just to make sure. I will see
Mr.
you all next week.
What was the answer to the last question, like the final answer?
85 kilojoules.
Thank you.
No problem. Anyone else?
Thank you, Professor. Hi, next weekend.
You too,
Thank
Baham.
you.
Thank you. Appreciate you guys coming. Let me stop sharing this now. And let's do stop share. It looks like I'm the only one here, so I will say bye-bye.